Hi, my name's Paul Callan. I'm the CTO of TerOpta, and these slides are going through a case study that we recently did comparing the performance of TerOpta's low-cost outdoor air quality sensors, Ambiex, against the official reference sensors, the AURN network, at various sites in London. We did this during what we called a high pollution event that occurred in late March 2022. The situation was that the Mayor of London issued a specific warning about a high air pollution level that was going to cross London and the southeast for several days, which might impact the health of various vulnerable groups. And we decided to track this using TerOpta's Ambiex monitoring units, which happened to be either co-located with or very close to government AURN monitoring stations, and we chose the three sites here: Elephant and Castle, Old Kent Road, and a site in Coffee Street in Deptford. The key pollutant we were looking at was nitrogen dioxide, NO2, because this is one of the main health affecting gases, and of course as well it's very hard to measure in such small concentrations with low cost sensors. And so we wanted to see how well the Ambiex monitoring corresponded to the AURN reference levels, although it has to be said the reference sensors are also imperfect, and therefore there's inaccuracy with those as well. The graph here shows two curves against time over a period of 4.5 days. The vertical axis is micrograms per cubic meter, and we're showing the blue curve, which is the Ambiex output, and the orange curve, which is the co-located AURN. And you can see that there's very good correlation between the two, and the pollution event is described very well, even if you only had the Ambiex low-cost sensor. There are a couple of rogue points here which are due to RF interference, radio interference, possibly a few smaller negative going points as well. This is because of the early nature of these models. These are prototypes. There is a later design which eliminates this, but even with those you can see that the pollution is described very well. This is a different kind of graph. It still concerns nitrogen dioxide at Elephant and Castle, but instead of plotting it against time, we're plotting the output from the Ambiex sensor against the simultaneous output from the AURN reference sensor. The ideal plot is a straight line of y equals x. Obviously in real life it's not like that, but the more closely it resembles that, the better the sensor. Here we've plotted a trend line, and you can see the slope and the offset. The offset of 2.7 micrograms per cubic meter is not much more than 1 part per billion in terms of gas concentration, so that is a very good offset. The slope of 0.8 is within industry norms, but we could potentially calibrate this sensor by applying a slope correction, which would bring that closer to unity. That has not been done with this one. No slope calibration has been applied, but even without that, straight from the factory as it were, the slope is still within industry norms. The R squared, the goodness of fit here, is 0.9, which is excellent actually for a low-cost gas sensor. Moving on to a different site now, this is Old Kent Road. Once again plotting NO2 against time for both the Ambiex sensor in blue and the AURN in orange, and once again the Ambiex unit is very well representative of the pollution event that's occurring. There is a little bit of evidence of the occasional radio interference related spike, which is eliminated by the new design, so you might expect some deviation when we come to plot the two sensors against one another. Similarly as well, you can see that the rising and the falling, where there are rapid transitions, it appears the Ambiex unit is reacting more quickly to changes in the concentration of the NO2. So again, in those rapid rising and falling events, we might expect to see a greater deviation between the two sensors. So here is the scatter graph of the two sensors plotted one against the other. Here you can see that there are some points a long way above or below the line due to the short rapid periods of change that we mentioned on the previous slide, the time lag between the sensors, and possibly a little bit to do with RF interference. But even with that, the R squared is 0.82, which compares very well within the industry and is a very usable figure. The slope of 1.09 is acceptable. It shows that the sensor sometimes overestimates, but within a sensible degree, and the offset is very good as well. Finally, moving on to Deptford. This is the time domain plot, and here the sites are actually about 80 meters apart, so the reference sensor and the Ambiex sensor are different in their location by about 80 meters. Normally, for a co-location test, you try and put the inlet of one sensor within a meter of the inlet of the other sensor. So for an 80 meter distance, this is giving a very, very good correlation. And the reason it's so good actually is partly because of the performance of the Ambiex system, but also because the pollution in this case is all coming from elsewhere. It's not local, it's not hyper-local pollution, so it should read the same. Here's the corresponding scatter graph. The R squared of 0.84 is very good. The slope and the offset are also good. There are some larger discrepancies which, looking back at the time domain plot, actually are due to the time difference between the responses of the two sensors when there is a rapid change, and that was the same with the Old Kent Road graph as well. Up to now we have been looking at nitrogen dioxide, NO2, because that is one of the most important pollutants for human health, and also because at these very low concentrations it's actually very hard to measure, especially with a low-cost sensor. But another very important type of pollution is particulate matter, in particular PM2.5, which is particles up to 2.5 microns in diameter. So because we do monitor that on all Ambiex units as well as NO2, I thought I would have a quick look at that before closing the presentation. So here's an example from Elephant and Castle. And you can see again the blue line is the Ambiex unit, and the orange line is the output from the AURN, and you can see excellent correlation, and the pollution event that we're looking at here has been described very well. Here's the scatter graph. This is one of those occasions where a human being such as myself may not have drawn the trend line in exactly the way it's been presented here in the automatic way it's calculated. So the slope of 0.86, although that is an accurate slope, I may have actually estimated it being slightly closer to 1. The offset of +6 likewise would be smaller if we repositioned the trend line slightly. But even still, it's a good slope and offset to have. The R squared of 0.94 compares very well within the industry for a low-cost particle sensor, and this is again a very usable sensor. So just to wrap up with a few conclusions, there's good correlation between the Ambiex low-cost sensor system and the AURN reference system that we observed during this high pollution event. We also can conclude that if the pollution is not local pollution, but it's from somewhere else and it's not coming from the immediate environment, then physical distance between the AURN and the unit under test is not as important, which is why the Deptford measurements were so good. And the other thing to bear in mind here is that these NO2 sensor elements have been out there working for about 18 months, and they're still working very well. There's no apparent evidence of aging, which was pleasing to see. Thank you for your attention. If you found that informative and would like to know more about TerOpta or about the Ambiex air quality monitoring system, then you can find us at our website, and also you could email us at the email address shown on the slide. Thank you very much.